last class, the majority of the time we were talking about the way electromagnetic radiation behaves. We learned about a very important thing called the photoelectric effect, and you should definitely take a look at that video to get that information. But going forward, the rest of this chapter has to do with this term periodicity, really, and that's what the title of the chapter is. But what that means is electrons, where their locations are. So we're going to learn, the first thing we're going to go over is quantum numbers and their orbitals, subshells, and all that good stuff of where the electrons are placed in the atom. That's very important. We can actually determine, we can take that concept and bring it to the periodic table and talk about electron configuration, which we're also going to do. And then we're going to take those concepts of electron configuration and really get into the detail of, because an atom has a certain electron configuration, it then has X and Y properties, meaning, let's say it can accept an electron very easily, which means it has a high electron affinity. Its radius, its size is determined by its electron configuration based on how many orbitals and how many energy levels that the electrons take up. So there's a lot of things that can stem off of electron configuration that we can figure out about these atoms, about the elements, just to make everything better for us. So let's go into one of the key concepts that we talked about was that electrons are located in what we call energy levels, right? And here's a good representation of that. You see the hydrogen atom, and it has these energy levels, n equals 1, n equals 2, n equals 3, and it goes really to n equals infinity. So there's an infinite amount of energy levels, but the electrons only take up certain ones. And then the identity of that element determines where the electrons are, at least at ground state. Once something is excited, you can have the electrons jump to different energy levels, the higher ones, but that's a different story. Now, the electron positioning, now these energy levels are really a construct of things that people made. So what that means is it's a model. Now, in reality, the electrons don't occupy strict energy levels like these orbitals. Like you see there's an orbit, right? There's an orbit around the nucleus, just like the planets around the sun. They're not that rigid in their path. They're actually going all over the place. But the probability of an electron being closer to the nucleus, if it's, let's say, a 1s electron, meaning an energy level 1 and in the s orbital. If that's the case, then it's probably going to be most likely in the center. And that's true. So what we can break that down into, the electron positions are determined by a probability distribution, meaning at most likely it's going to be in some distance away from the nucleus, but sometimes the electron might be further away. And the probability of it being further away decreases as you get further away, right? So if you have a 1s electron, which means it's in the n equals 1, energy level 1, very close to the nucleus, the chances of it being really far away is very small. It could happen, but it's very small. So that's what we mean by probability distribution. They're not set to these rings. They're kind of all over the place, but we use the rings to simplify it for us. So let's take this into the main concept of the first main concept, which is quantum numbers. Now, that term may be foreign to a lot of you. It may not have any meaning. And I know when I heard it for the first time, I didn't know what it meant. But the best way that it could be summarized is the quantum coordinates. Or if you want to get rid of the word quantum, if it's too complicated, just say the coordinates. It's really the coordinates of the electron having to do with its actual position and its energy. So if you have an atom with 50 electrons, they all have different quantum numbers. Every single one has a different set of quantum numbers. And these quantum numbers, there's 4 of them. And that's the coordinate plot for them. So the first one is the principal quantum number, which basically means the energy level, and that's denoted by N. So N for energy level. Energy level, we already saw one of those with N equals 1 over here, 1s. That means it's 1. So that's just, we're going to get into each one in more detail, but that's just the principal energy level. The second one is the angular momentum quantum number. So this more or less has to do with energy. And it tells you that which subshell, or it tells you which orbital that the that the electron is in. So within each energy level, there's multiple orbitals. And we note these orbitals by letters. There's S, P, D, and F. Those are the orbitals. There's 4 of them. Now, this angular momentum quantum number, L, has rules. And we'll go over the rules in the next couple of slides. So there's parameters that it has to live by. So though the parameters for L is it has to be between 0, the number 0, and between n equals or n minus 1. For example, it's a range. It could be any number in that range. For example, if n equals 2, L has 2 possible values. L equals 0, L equals 1. So it has to go from either 0 all the way through the range of n minus 1. So there's a possibility for it. And we'll break down what these possibilities mean in terms of the number of electrons that can maximally occur in a specific energy level and in a specific atom. The third one is the magnetic quantum number. So this quantum number represents like magnetic properties, really magnetic properties of the electron. Not really important what it represents, but it's one of those coordinates. And it's annotated by ML. So sometimes you write it like this. I write it like this, ML. This L I write like this. So ML, and ML has certain rules too. So ML's rule is that it could occupy the range of negative L to positive L. That's a range. So it can be whatever L is, it could be the negative version of that, any number in between to the positive version. And then just to write the rules for L to be consistent, it would go from 0 to n minus 1. Any number in that range. The next is a spin quantum number. The spin quantum number represents the spin, right? So electrons, the thing about electrons is every subshell so the way the breakdown works is that there is energy levels, which we know, right? That's denoted by N. There are subshells, which are denoted by L. There's magnetic positions in those subshells, which really mean ML, we call them lobes. There's different lobes of each of the different number of lobes in the orbitals. And we'll get to that when we see it graphically. And then there's a spin, which represents the likelihood of 2 electrons being near each other in the same subshell. So the possible values for spin are just -1/2 and +1/2. There's only 2 possible values. It's either one or the other. What this means, why 1/2, I don't know. But basically, one of them means it spins up, one of them means it spins down. So if you have 2 electrons that are in the same quote-unquote lobe, they have to have this spin of either minus or plus, or -1/2 or +1/2. One of them has to have one of them has to have the other. If 2 of them have the same spin, they can't be next to each other. That makes a big repulsion force between the electrons. So these are just the rules for MS. There can only be, it's -1/2, +1/2. Okay, so let's get into each one of these and I'll ask for questions. So principal quantum number N, it's the principal energy level, right? So it means energy level 1, 2, 3, really, etc., anything. And it relates to the size and the energy of the orbital. Meaning, if you have energy level 2 versus energy level 3, energy level 3 can hold more electrons because it's bigger. And elements that use energy level 3 compared to energy level 2 for their valence electrons are going to be bigger. So, yeah. And as you increase, important thing is, as you increase the energy levels, the electrons become less tightly bound to the nucleus. Because what happens is what we call electron shielding. So let's draw a proton, or let's draw a nucleus. The nucleus is positively charged, as we know. And let's draw 2 energy levels. Electron number 1, electron number 2. Let's say the charge in this nucleus is +2, right? So it's neutral. So what charge, so if I was this electron what charge do I see? I get attracted to +2, right? This is -1. I get attracted to +2. That's a pretty strong attraction force. This guy up here in energy level 2, I could also get attracted to the nucleus. But look what's in my way. This guy's in my way. So if you take that into effect, what this electron, this outer electron, is actually seeing is it's getting pulled in by a +1 charge, not a +2 charge, because it has to first wait for whatever force is left after this attraction force happens with the inner electron. The remaining force, the remaining positive charge, is used to pull in the outer electron. This is called electron shielding. So one electron could shield another one and make the nuclear charge less. And we also call this the effective nuclear charge. So the effective nuclear charge represents the actual charge that an electron is, if you were the perspective of the electron, the charge that it's seeing in the nucleus, after it takes into the account the electrons that are before it that kind of shield the nucleus away, or shield the positive charge away from that specific electron. So this is why energy levels are important. We need to see where the electrons are, how much repulsion, or not how much repulsion, how much attraction they have to the nucleus, or how little attraction they have to the nucleus. And also, we can use these energy levels to organize our electrons once we become larger in molar mass and larger in size as elements. Any questions on this one? No? Okay. All right, next one is angular momentum quantum number L. So L has these rules. N can be any integer, but L cannot be. L has the rules. It can go from any integer value of 0 to n-1. Very important. That won't be given in the exam. You have to know it. 0 to n-1. And these numbers aren't just random. They mean something. These numbers are assigned to the orbitals. They're the value that tells you which orbital the electron is in. So, for example, if L equals 0, that corresponds to S. If L equals 1, that corresponds to P. If L equals 2, that corresponds to D. L equals 3, F. And we're not going to focus on G. There is no G on the periodic table, but you can have elements that, or you can have electrons that jump to G. We're not worrying about that in this class. So, easy way to remember it, SPDF 1, 2, 3, 4. So, SPDF 1, 2, 3, 4. That's for L. And it tells you, based on the L value, it tells you which orbital it's in. Okay, the next one is magnetic quantum number ML. This tells you more or less what subshell it's in. So after that, or the rules for this, it has rules as well as parameters. The parameters would be between positive L and negative L. So if L equals 2, for example, what are the positive values of ML? If someone could tell me, or write it. Anybody? Positive values for ML if L equals 2.
-1.
Good. So I heard things. Lucas, I think you're right. If that's, oh, no, not. No. Okay, so the range, I don't think anybody got it right. Okay, so the range of possible values is from negative L to positive L. The entire range, it could be anything in that range. And let's say L equals 2. So what are the possible values? Eric, that's a good start. -1 and +1. What else? 0. Yep. There's 2 more. Good. Good job, Alex. -1 and plus, or sorry, -2 and +2. So if you have L equals 2, the options for ML are -2, -1, 0, +1, +2. It has 5 options for L equals 2. Does everybody understand that? Yeah, okay. That's important. These 5 options tell us about what we call lobes and subshells. Okay, now if we look at what we saw before with the value of L, what is L equals 2? So I use L equals 2 as an example. L equals 2 corresponds to this thing called the d orbital, which we didn't get into yet, which it's one of the orbitals. You have S, P, D, and F. It's D. So I'll tell you right now, the d orbital can hold a maximum of 10 electrons. This ML number tells you how many sets of 2 electrons can fit in this energy level subshell. So I'll say it again. The number of MLs tells you not their number themselves, not -2, -1, 0, 1, or 2. The number of their choices. So how many choices are there here? There's 5 choices, right? There's 1, 2, 3, 4, 5. There's 5 options for ML. The number of options of ML directly tells you, if you multiply it by 2, the maximum number of electrons allowed in that orbital. That's why D can hold 10 electrons. And that directly corresponds to the periodic table, which we're going to see later on. And a good question would be, oh, why multiply by 2, Professor? And the answer has to do with the 4th quantum number, MS, which is the spin. Because in each one of these subshells, in L equals 2 case, you have 5 possible subshells, -2, -1, 0, 1, and 2. In each one of those, the magnetic spin, the spin quantum number could be +1/2 or -1/2, meaning one can spin up or one can spin down. This means that each subshell has 2 possible states of electrons, one going up, one going down. So if you were to fill this orbital up, the maximum number of electrons it can have would be 10, because in each one of these MLs, you'd have one spinning up and one spinning down. So it would be the number of MLs times 2. That's how we got 10. And that corresponds directly to the periodic table, which is super cool, which we'll see. Any questions about that? No? Okay, cool. All right, so let's see this in action. Good. All right, so let's see this in action. We have different cases. So we have N equals 1. N equals 1 is the smallest energy level, right? And it can't really hold too much. It can only hold 2 electrons. How many? So there is no E, there's F. So F, and good, Harrison, great job. F would have 14, perfect. So for energy level 1, the only possible L value is 0, right? Because L can go from 0 to N-1. So if it's 1, that means it can go from 0 to 0. That means the only option is 0. That means that in N equals 1, there's only one possibility for an orbital, and that's an S orbital, and we call it 1s. Because the 1 comes from the energy level. There's also 2s, there's also 3s, 4s, 5s, all the way up to 7s. And this, the initial number, 1s, 2, 3, 4, that comes from the energy level. That tells you how far away from the nucleus these electrons are. So once we get to configuration, it's going to be like a puzzle. It'll be a lot of fun for you guys. And I'll give you some examples to do. So then let's look at N equals 1 again. The only possible value is L equals 0, which corresponds to our S. And so you have 1s. The only possible ML value is 0, meaning it has 1 orbital, 1 subshell, and each subshell holds 2 electrons. So you multiply it by 2, 1 spinning up, 1 spinning down. That means that this S orbital has a maximum capacity of 2 electrons. And that's true for every single S orbital, no matter what energy level it's on, 1s or 5s. It can only hold a maximum of 2 electrons. So keep that in mind. That's why every S orbital only has 1 ML value it corresponds to, and that's 0. So you multiply the number, remember I said you multiply the choices of MLs by 2, and you get the number of electrons possible in that orbital. So just like Harrison said, in F's case, so 4, energy level 4 is the first place that F comes in. So if you count those, if L equals 3, that means ML is -3, -2, -1, 0, 1, 2, or 3. So those are 7 choices. You multiply the 7 choices, each one has in each choice, you have 1 electron spinning up and 1 spinning down. So that means you have 14 electrons possible.
Professor?
For a D, yes, question.
It's just I don't really understand that. Can you do an exercise? So, because everything that I learned is such in the air, I can, like, you know.
Okay, yeah. So we're gonna talk about the other orbitals right now too. So hopefully it'll make more sense. So let's talk about P. So the P orbital. Let's backtrack. We'll go here. We'll go right here, right? So you have energy level 2. That means not energy level 1, but energy level 2. So you're kind of further away from the nucleus. Because of the rules we just learned, when you have energy level 2, the possible values for L are 0 and 1. And we know that because the rules for L tell us the possible values are from 0 to n-1. So for n equals 2, you have 0 to 1, because n-1 is equal to 1 if you have n equals 2. Okay, so now let's take a look at the first one. For that L equals 0, that's the first case, it's an s orbital. We know that because of this chart where we went over L values of 0, 1, 2, 3, 4 correspond to SPDF, and also G. Don't worry about G. Let's just do 0, 1, 2, 3. So L is 0, 1, 2, 3. The letter is SPDF. 0, 1, 2, 3, SPDF. Okay. So next would be in that s orbital. So now we're at the s orbital. That means we have L equals 0. The only possible ML value is 0. L equals 0. ML, the rules for ML, the range is from -L to +L. And since L is 0, the possible values for ML are between -0 and +0, which mean just 0. So that means that there's one subshell. One subshell. That subshell holds a maximum of 2 electrons. Each one of them holds 2 electrons. So in P's case, you have 3 of them. Each one holds 2 electrons, maximum of 6. But in S's case, there's only one. It holds a maximum of 2. So that means the maximum number of electrons is 2 in the s orbital. In every s orbital, it's 2. So next will be P. So let's talk about P. Now, the first time that a p orbital occurs is when n equals 2. And the reason why is because that's the first time that, based on the rules of L, that you can have L equals 1. Because if you go up here to energy level 1, you can't have L equals 1, and so you can't have n equals 1, L equals 1. That's not possible, because it conflicts with the rules. But for n equals 2, you can have L equals 1. So that means, since you have L equals 1, remember 0, 1, 2, 3, SPDF, same thing. You have 0, 1, SPDF, so SP. So that means your L equals 1 means it's a p orbital. Since it's an energy level number 2, 2p. That's why we have 2p written there. And for that L value of 1, the possible ML values are -1, 0, and +1, meaning there's 3 subshells that can be broken down into 2 electrons each, which means a total of 6 electrons max. Okay, questions? No? Okay, so for the d orbital, quickly, the first time a d orbital exists is when n equals 3, because that's the first time you can have L equal 2. When L equals 2, remember 0, 1, 2 for L, and then you have SPD. 0, 1, 2, SPD. That means D occurs. So that means you have a 3D orbital. And that 3D, since it's L equals 2, the possible ML values are -2, -1, 0, 1, 2. 5 of them. There's 5 possible values. So if that's the case, then the 5 possible values times 2, because one electron spins up, 1 electron spins down in each one, you have a possibility of 10 electrons. Okay, questions? All right, let's do practice. Oh, there's a question. Would you always multiply by 2? Yes, the number of ML values multiplied by 2 is the number of electrons allowed in that orbital. Always, because in that subshell, one has to spin up, one has to spin down. So you have to have 2, and I'll show you why it's 2. Well, I told you why, but I'll show you real quick why I'm talking about one spinning up, one spinning down. So here's what the orbitals look like. I mean, here's a model, right? They don't actually look like balloon animals, but here's what they are. So this is the D orbital. It's kind of more. Let's talk about the P. Here we go. So the P orbital, right? It has 6 lobes. So they're like dumbbells, right? Each dumbbell has 2 lobes, a positive one and a negative one. It has 6 lobes. Each one of those lobes would occupy 1 electron, or 1 electron would occupy each one of those lobes. So you have 6. There'd be electron here, electron on the z-axis, bottom z-axis, plus y, minus y, for a total of 6 electrons, like that. So if we drew all of these pictures on top of each other, it would look like this. So that's why we're doing these. That's why, and the ML value for P, there's 3 ML values. Either this would probably be -1, 0, +1. That's actually how it works. That each one of those ML values corresponds to one of these dumbbells. And each one of those dumbbells can hold 2 electrons, electron 1, electron 2. So hopefully that clears it up. Okay, so question. So for principal quantum level n equals 5, determine the number of allowed subshells, that's the different values of L, and give the designation of each. So what that means is, for, let's say, I'll do one of them for you. So for n equals 5, we'll do it together. What are the possible L values for n equals 5? Who could tell me?
0 through 4.
Perfect. 0 through 4. So there's 0, there's 1, there's 2, there's 3, there's 4. Okay. So determine the different values of L. We did that. So these are L. Now, what does 0 correspond to? What letter orbital? We have S, good. 5, good. It would be 5s, good. Then we have, oh, so Isaiah, not 1s. So, and James, you're right, S. So in energy level 5, we would call it 5s. And since we're in energy level 5. So when we're going to be writing for the configurations, we're going to be writing 5s something, 5p something, 5d something. That 5 corresponds to the energy level that's in. So then we have 5s, 5p, 5d, 5f, and then there's 5g. Oh, 5g, like the cell phones. But that's whatever. We're not going to focus on G. It's not represented in the periodic table. But anyway, that would be the answer. It would be all of them. 5G is also there for the answer. But this would be the designations, meaning like what exact orbitals do we have? Now, take a step further. What are the possible ML values for, let's say, L equals 3? How many possible ML values? Actually, no, don't answer that. Well, you can answer that in your head. But more specifically, how many possible electrons does that correspond to? L equals 3. Good, 14, right. Because the ML values, there's 7 of them. There's -3, -2, -1, 0, 1, 2, 3. That's 7 of them. Multiply that by 2 because there's 2 electrons in each lobe. and you get 14 possible electrons. So we can use this to figure out a lot of stuff, to be broad, but yeah. Anyway, so yeah, you come up with those 5s, 5p, 5d, 5f, 5g. Okay, so what are the possible values for? Okay, whatever. That's, here we go. We'll do this one. So how many electrons can be described by the quantum numbers n equals 3, L equals 3, and ML equals 1? They don't have MS here, but just assume that it's either spinning up or spinning down.
Wait, so wouldn't it just be 0 since you can't have n equals 3 and L equals 3?
Perfect. Good. It would be 0. But to answer Johnny's question, it's okay, James. To answer, because a lot of people were thinking that. But to answer Johnny's question, the reason why I started counting from 3 here is because I picked 3. I picked L equals 3. So I said, oh, if L equals 3, how many electrons can that hold? So the ML has to be either -3 all the way up to 3, multiply those choices by 2, meaning there's 7 choices, multiply that by 2, and you get 14. But going back to here, so I guarantee you right now, on the test, there's going to be a question, or on the final, there's going to be a question on this saying, which of the following is not a possible set of quantum numbers? They always put that on there. So what you do is you see, okay, which set of quantum numbers doesn't follow the rules? N equals 3, that's good. L equals 3 when N equals 3, no way. ML is 1, sure, that works, but still, this can't work. So to make this right, you'd have 3, 2, and 1. That would work totally fine because L is within the parameters it can be. Even 3, 1, 0, that would work, or 3, 1, 1, that would also work. So it's important to know those rules, to know what combinations can and can't work. Okay, any questions on that before we go over the shapes of the orbitals quickly? All right, let's go. We can do this. Don't fall asleep. All right, so the s orbital, it's small. And it only holds 2 electrons. That's really, honestly, that's really all you need to know about it. It holds 2 electrons and it's small. It's got one, it's spherical too. It's got 1 lobe. So if you draw an X, Y, Z axis, it just sits like in the middle. And then there's bigger ones too. Let's say this is 1s, 2s looks like this, but it still energetically only can hold 2 electrons. And it's like that. Okay, next one is p orbitals. So p orbitals have 2 lobes separated by a node at the nucleus. I don't like that terminology. I'll just show it to you. That's what it looks like. So you have a dumbbell along each axis. You have a dumbbell along the X, dumbbell along the Y, dumbbell along the Z. And each one of those, let's say if you use gym examples, if it's a dumbbell in the gym, each one of those weights on either side of the dumbbell holds 1 electron. So you have 1, 2, 3, 4, 5, 6. So 6 possible electron positions within a p orbital. That makes sense? That's why you can have 6, because of the shape of it. D orbitals. It's basically like a p orbital, but with 5 lobes. And here we go. So the first 4 make sense. Oh, it's just like balloon animals, but you have 1 electron here, 1 electron, and this is more like spatial arrangement. But you have like 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Yeah. And then the 5th one's weird. It kind of goes around. That's because of like the energetic favorability. And also that's also due to a lot of, when you get to this, putting electrons into this orbital, there's a lot more electrons already in the atom that are making the shapes of their orbitals different. But just know that there's 5 of them. Each one of them holds 2 electrons for a maximum of 10. That's really it. And then F is really crazy. Just know that max of 14 electrons. Max of 14 electrons. Just know that. Very important. Okay. So the main thing that determines energy is important. The main thing, and it kind of makes sense, the main thing that determines energy is energy level. Well, no duh, professor, but yeah, it means more than the type of orbital, meaning SP or D. So if you have 3D, for example, it's going to be less energy than 4s. That's important to mention now, because when we do the configuration, we're going to be passing through atoms that have electrons in 4s before we occupy 3D. And these electrons would be the valence electrons, because they're the furthest away in those types of atoms. But the idea here is that as soon as you jump an energy level, there's a big jump in energy. Oh, yeah, that makes sense. Well, yeah. So, but here's where it gets complicated, though. There's always exceptions to this stuff. When you get to energy level 5, 6, and 7, the energy gap isn't big enough. Isn't that big? They start to close. They start to get closer together. So if you get up to like, here's where it gets really weird. If you get to 4F, which would be like here, and then 5D. 5D is like here. Like 5D is a teeny bit higher, but they're very, very close in energy. What happens is electrons don't know where to go, and they can actually go to either one. Since they're so close in energy, the 5D and the 4F. So once we learn about electron configuration of the lanthanides and actinides, the ones on the bottom of the periodic table in that their own little enclosure, rectangle, those are the ones that have weird electron configurations. And there's actually still dispute about their ground state configuration because of this phenomenon, that the energy levels, when you get to this high in N, so in this case you have N equals 4/5, when you get above that, it gets weird. But for everything lower than that, it makes perfect sense. Okay. So let's see this one. So a ground state electron in the hydrogen atom is given just enough energy to get to N equals 2. So when you give it, so energy level 1 is where the hydrogen atom electron stays. But if you give it enough energy to go to 2, which orbital will it apply? Well, not apply. Which orbital will it occupy? Do we know? What do you think? A is a good guess. A is a good guess. But Daniel, you're on the ball. E. So what we just learned is that based on this chart, the energy gap between orbitals in the same level, let's say N equals 2, they're all very, very close. That's why I mentioned this weird example, because they're all very, very close. When they're very, very close, that means if you kick an electron to, well, you can argue this. You can argue 2s because not based on what's actually true. It does have a little bit less energy than 2p. But in general, they're very similar compared to the other energy levels is what they're trying to say. So technically you'd have they're equally likely. That's what you would say, because all the energy level 2 orbitals, S and P, they are on basically the same amount of energy. They have the same amount of energy. Okay. So we talked about the spin already. There was reiterating spin. Do you have a question? Oh, so X, Y, and Z just means the planes. So you can have remember we had 3 dumbbells of the P. One of them was on the X-axis, one of them was on the Y, one of them was on the Z. And then when you get to the D orbitals and the F orbitals, they make up weird axes. And like for the D orbital, you have dxz, dyz, dxy, dx squared minus y squared, and dz squared. So those are just the three-dimensional planes that they occupy. Oh, and Harrison, 10. Max electron d orbital is 10. Okay, so talked about this already. Now, the Pauli exclusion principle. And this we kind of already alluded to, that no two electrons in the same element could have the same set of all four quantum numbers. So if they have the first three quantum numbers is the same, let's say they have n equals 3, L equals 2, ML equals 2. If all those three are the same, then the MS has to be different because one of them has to spin up, one of them has to spin down. That's important. So an orbital can only hold 2 electrons. They must have opposite spins. So one spins up, one spins down. And here's an example of that. So you have external magnet. Oh, external magnets here, and then they create a magnetic field. So if you spin in one direction, the magnetic field's in the opposite direction if it goes in the other one. So these would come close together since they have the opposite magnetic fields. They would be more likely to be in the same orbital. So it helps them. That's why they need to spin in opposite directions. If they spin in the same directions, they have a very strong repulsive force. Okay, so let's do another question. So which of the following quantum numbers is not allowed? Which combination, A through E? And some of you answered already, and incorrect. The answer is A, because, oh, look, we encountered the same rule again, where L can only be from 0 to n-1. So for L equals 1, you can't have a p orbital. The only option is 0, which is an s orbital. We know that. So good. All right, so this is energy levels again. Yeah, so when the electron is placed in a particular quantum level, they prefer the orbitals in what order? We also talked about that, alluded to it. So what order do they go into? If they had to pick one. C, yes, SPDF, perfect, SPDF. And quantum numbers relating 0, 1, 2, 3. All right, now let's just take everything we learned about, all right, we have all these different energy levels. We have their L values, which tell us their number, or their letter, S, P, D, or F. They have their spin and all that stuff. Let's relate it to the periodic table. So look at that, boom. So this is the periodic table annotated with the orbitals. So you can have your s orbitals, your p orbitals, your d orbitals, and your f orbitals. And there's a lot to go over here. But first, to get the majority of the elements' electron configurations out of the way, let's talk about sulfur. We're going to do the electron configuration for sulfur. We'll make sure, let's write neon here too. So we'll do sulfur first. I'll show you why I wrote neon. So sulfur. The way we write configuration is we're going to start from the top left, hydrogen, all the time. Then we're going to count. 1s1. So and keep in mind, each of these boxes, look at how many boxes there are. For S, there's 2 boxes. Each box represents an electron, right? Because when you go across the periodic table, you gain protons and you also gain electrons. So each box represents an electron. Then, or each box in the periodic table. That's very important to know. Then each p orbital has how many boxes? 1, 2, 3, 4, 5, 6. How many electrons does a p orbital have? 6 possible. Makes perfect sense. If you want to look at D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. So we know that a d orbital has a maximum of 10 electrons. And then for F, we know it has a maximum of 14. And this is weird because on some periodic tables, they show 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The reason why is because these 2 elements, actinium and lanthanide, some people say they're in the F orbital because that their electrons, since the energy levels are so close between 5 and 6d and 4 and 5f respectively, then some of the electrons don't exactly know where to go. And it has to be determined experimentally. It doesn't really make sense according to the trends that we know, but there's some weird rules with that. But in terms of lanthanides, you're not going to have to know the configuration of the lanthanides and actinides. That shouldn't be expected, or that's not expected of you, because that's ridiculous. Okay, so for sulfur, move this up. Okay, for sulfur, what we're going to do is we're going to start at the top. 1s2. That 1s2 tells us n equals 1. The s tells us L equals 0. And the 2 tells us both electrons are filled. Both. Meaning this one and this one. That's helium. Then 2s2. So we skip, we go to the next line. 2s2. So we write 2s2. Then we skip across. 2p6. 2p6. So this is all gone. Then 3s2. 3s2. Nothing here. Skip it. 3p, not 6, but 4. Because that's where sulfur is. 3p6 would be over here. Argon. We don't want that. We want sulfur. So it'd be 1, 2, 3, 4. So 3p4. 3p4. Okay, and ta-da, that is the electron configuration for sulfur. Any questions on that? That's very important. That's a basic one. There are a lot of rules to it, but it's a basic one. Any questions? And there are comments. I'm not understanding. Okay, so we're gonna do more examples. So let's take this into what we already know, and we'll show you why it makes sense. Let's talk about total electrons. Sulfur, the element sulfur, has 16 electrons. The reason why I know that is because the atomic number is 16. Got it, right? Because it's atomic number 16. So I have 16 protons, 16 electrons. What we just did is we determined the positioning in all the electrons, all of those 16 electrons, using this notation. This occupying the orbitals in order. And the exponents, they're not really called exponents, but the top numbers, the superscripts, are the number of electrons in each orbital. So 1s2, meaning there's 2 electrons in 1s. 2s2, 2 electrons in 2s. 2p6, 6 electrons in 2p, etc. If you add these up, what do you get? 2 plus 2 is 4, plus 6 is 10. Plus 2 is 12. Plus 4 is 16. And look at that. Sulfur has 16 electrons. So we just took those electrons that we knew existed and categorized them into orbitals. That's why we're doing this. Why do we need to, and a good question would be, oh, okay, why do we need to do it though? Like, I get how to do it, but why do we need to do it? We need to do it because this tells us important information about how the sulfur is going to behave when it comes to gaining or losing an electron. So this tells us, oh, the 3p is almost already filled. So if I have 2 more electrons here, sulfur would probably like that. That's true. And then we'll get into more detail about that later, and it gets a little bit more tricky, but that's for now. So questions is on this. So what about it is confusing? What part don't you get if you don't get it? Anybody? We're gonna do more. All right, let's do another one. Okay. Oh, now chats. Okay. Okay. If you have more questions, you can email me. We'll set something up. All right. So let's do another one. We'll do cadmium, since it's written there. And Alex, correct. It's like reverse engineering based on knowing the atomic number. You're finding the element first, and then you're basically counting up to it. And keep in mind, on the test, that's why we have to do a lot of practice at this, because on the test, you're not going to have 3D, 4D, all that stuff written. It's just going to be a normal periodic table that you can barely see to make fun of the system and their periodic tables. All right, so let's do another one. All right, cadmium. Cadmium. So how many electrons does cadmium have? Anybody want to tell me? I'll look it up. Cadmium atomic number, 48. Okay, 48. So we know it has 48 electrons and 48 protons. Let's do the configuration for it. Okay, so we start from the top every time. 1s2, 1s2, 2s2, 2s2. Go across, 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 going all the way through 2p. So we're not going to stop reading the periodic table and writing stuff down until we get to our target element, which is cadmium. So 2p6, we're at neon. 2p6. Then 3s2, 3s2. Keep going, keep going, keep going. 3p6. 3p6. We're right here now. Next line, 4s2. 4s2. Next line, now you have 3d10. So you write 3d10. You're going all the way through it. 3d10. We'll talk about why that happens in a minute, where it goes from 4s to 3d to 4p. But if you memorize a table as d starts at 3, you're good. But let's keep going. So we're here right now. 4s6. Nope, 4p6. My bad. 4p6. Now we're right here. Next line, 5s2. 5s2. Next line, 5s2, we're right here. Now we finally have cadmium. We have it located in the orbital, and it is in 4d10. Boom, done. So we counted all the way up to cadmium. That's a lot of stuff to write, but there's an easier way to do it. Now, before we go over that, any questions? And this works for all the elements. There are some that don't follow the rules exactly, but we have to think about it a little bit more. Yep, that's basically it, Logan. Yep, you count up across and that's exactly it. So if you count up I'm not gonna do it right now, but if you count up these exponents, you're gonna get 48. That's just to check your work. That's not the answer. So that's not the questions they'd be asking for. They wouldn't ask you for how many electrons are in cadmium +1 or cadmium, just ground state, because you could look at the table and figure that out. They're gonna ask you is how many electrons in 3D does it have? How many electrons in 4D does it have? How many electrons in 5P does it have? For cadmium's case, it'd be none because it doesn't reach 5P. They might ask you, which one of these are the valence electrons, or how many valence electrons does it have at ground state? And Johnny, yeah, the N, M, and L, all that stuff, that relates to this, but this is how you're actually going to apply that knowledge. So it's important to understand both of them. But if I had to pick, I don't know, there's gonna be questions on both. So Logan, yes, if there was how many electrons are in 3D, the answer would be 10, right? Because it's located in the position 3D10. All right, so that's that. Now, a good question, if you guys were thinking about it, is, that seems like a lot of work. What if we have an element down here in like 7P or something, and we don't want to write all that stuff? Well, there's a way around that. So this is what we call the abbreviated configuration. Now, you can abbreviate this configuration for any element, really. And the way to do it is you take the element that you're abbreviating, take the element, and you go backwards. Watch my cursor. We go backwards, we go back, all the way up over here, all the way up over here to our last noble gas. Noble gases are all 8A, noble gases. The last noble gas that we have is I think this is xenon. This is argon. Yeah, so it's xenon. And Eric, yes. Yeah, that's the same thing. It's a different order. But yeah, that's the same configuration as cadmium. Sometimes they might have different order. Sometimes they might put the 5s in the front because it's the valence electrons, since it's the highest energy level. But as long as you have everything, there's no right order to write it in, or correct order to write it in. Anyway, xenon. We're going to take the last noble gas that we passed through, and we are going to put it in a bracket. Like that. So what this tells us is that this is shorthand. It's telling us that, all right, this bracket means that every electron configuration up until xenon is covered by this bracket. So this bracket is the same thing as writing all of this, all the way from 1s2 to 4p6, because look where xenon's written in 4p6. So we can just write xenon instead, and then we can write the rest, which is 5s2, 4d10. Like that. Okay, any questions on that? That's called the abbreviated configuration. You can only do that with noble gases, meaning you can't write like carbon in brackets. So you can only count backwards. And yes, Logan, you can do that for any of them. So, and it's correct too. It's not like, it's not, they're identical. If you were to write either one on an exam, it would be correct. They're identical. There's no preference for one or the other. But for something like carbon that's located right here, you're not going to really need to write it. I mean, you can write helium in a bracket. That saves you like nothing though. You write helium in a bracket, and then you'd write 2s2, 2p2. You might as well just write the entire thing, which is 1s2, 2s2, 2p2. Same thing. And yes, good. Yeah. So Logan, for sulfur, exactly, it would be bracket Ne. So I'll write it on the bottom here. Sulfur equals bracket Ne. And then whatever comes next, which is 3s2, 3p4. It'd be just like that. So good. Okay. Any other questions on that before I go over the next concept? Abbreviate. Yes, you go back to the noble gas that you above it. Yeah. Okay. So another thing you can figure out from this configuration is how many valence electrons there are at ground state of a certain element. Now, the valence electrons are the ones that are in the highest energy level and the furthest away from the nucleus. So in cadmium, let's look right here. Let's highlight things. Let's look. That's not highlighter. Whoops. Here we go. Highlighter. Let's look here. This is cadmium. So how many valence electrons does cadmium have based on the configuration at the ground state? Valence electrons. So valence electrons are the ones that are the furthest away. So Daniel, good idea, but it's not 12. Anybody else? Good, Alex. 2. It'd be 2, right? Because even though, so this is the thing. Remember we learned that if you have a higher N value, higher energy level number, that means it's more energy than everything before it, meaning everything that's a lower energy level number. The energy level number takes precedence over everything else. So if you have 5 energy level, which that's what this is 5s2 versus a 4d10, even though when you're counting, 4d10 comes after 5s2, the 5s2 electrons are the valence because they have the highest energy level N value. They have 5. So in the energy chart, they'd be out here, whereas 4d10 might be like over here. This is 4p, and this is 4s. But 5 5s is all the way up there. So does that make sense? That you can figure out the valence electrons from this, and it was at every time it would be the ones that have the highest energy level, or the electrons associated with the highest energy level. Now for sulfur, what would that be? So let's look at, I'm going to highlight sulfur. Here's the electron configuration abbreviated for sulfur. How many valence electrons? Good, 6, Eric, nice. So the reason why it's 6, I mean, you knew it was 6 before this chapter began, right? Because you have 6A. 6A, 6 valence electrons. Boom. This is just confirming that because those electrons are located in 3s2, 3p4. Both of them are 3, and they're the highest out of everything that's in neon, which is all 2 and 1. Therefore, all of their electrons must be valence, which is 2 plus 4, or 6. Okay, so here's what we're going to do now. We're going to do some practice, and we're going to take a little mini break. So, oh, yeah, an Offbow Principle. Okay, we'll do Offbow Principle when we come back from our mini break. So let's do some practice. I'll leave this up. Actually, no, I'll put up a real periodic table. Periodic table. How am I going to do this? Split screen. Yay. Okay, so I'm going to write some elements. And it's tougher, so you should get into the habit, and you will with the homeworks, of doing the configurations without looking at the table that we were looking at before that tells you which ones it is. So in this table that we see on the right, you have like 1s, 1s2 is helium. You have 2s, 3s, 4s, 5s, and then D. So, oh, something I forgot to mention that's important. So if you look on the left, I know it's kind of sloppy, but the D orbital, you notice that it starts at 3, right? We already went over why it starts at 3, having to do with the quantum numbers, but it starts at 3, but it comes after 4s. So that's weird. After you add electrons to a higher energy level, you then add them back to a lower energy level. So that's weird, but that has its energetic reasons also. So it's important to just know for your exam and for navigating around the periodic table that D starts at 3. That's an easiest thing to remember. So D starts at 3. S starts at 1. P starts at 2. D starts at 3. F starts at 4. So 4F is the first F. So when you come into the F orbital, which is located over here, actually the F orbital comes after 6s. So why does that happen? That is also energetically favorable upon observation. That's what we can deduce from that. Actually, really no one knows. It's really just, we know it's energetically favorable and we observed it. So we go by those rules. That's real science. So yeah, so the 4F comes here, and then 5F comes here. So they come there. And they come after 6 and 7s. So just understand that if you want to talk about it in terms of the periods, period 1 through 7, D, the D orbital, all of it, the D block, lags 1 behind. So when you have period 4, the D would be 3. Period 5, 4D. Period 6, 5D. And then you could think of the F lags 2 behind of the period. Period 6, you'll have 6S, 4F. Period 7, you'll have 7S, 5F. So it lags 2 behind. That's just a little nuance. That's a good way to remember it. Okay, so let's do some examples. Figure out the configuration for calcium. Also, we'll do a couple of tricky ones too. Chlorine 1 minus, so the chlorine anion. Re, and then we'll do Re2+. All right, so calcium. We'll go through them a little bit quicker. So start at hydrogen, go to helium, 1s2. Then we're at lithium, 2s2, going through beryllium, boron to neon, that's 2p6. And then we're at magnesium, so it's 3s2, skip all the way across, 3p6. And then calcium is right here. I can't click it. I can't write on the web page. James, is there any time where you can't use shorthand? If they tell you don't use shorthand, but I don't imagine them doing that. If they say write the non-abbreviated configuration, then you can't write the abbreviated. But other than that, you can use it anytime you want. If they say write the configuration, you can write the shorthand. Okay. So 3p6, we're right at argon, and then you have 4s2. And that's where calcium is. So the shorthand would be simply argon in brackets, followed by 4s2. Any questions on that one? No? All right. Next would be chlorine. So we'll just do abbreviated for these. So chlorine, you can backtrack to neon, or the noble gas above it, neon. So we can write in a bracket, neon. And then whatever comes after neon, which is 3s2. That's the sodium and magnesium. 3s2. And then we go across to chlorine. Chlorine is located in the 5th position, meaning it's 3p5. So 1, 2, 3, 4, 5. And it's on the 3rd level of P. So 3p5. Now, what would chlorine 1- be? How would you change chlorine to make it chlorine 1-? What would you do? Good, Eric. 3p6, exactly. And that's exactly what happens during its anionic state. Remember, we talked about how when the nonmetals become anions, they gain electrons equivalent to their charge, such as oxygen is -2 when it gains 2 electrons to become a noble gas configuration. That's what I meant. I used that term before, noble gas configuration. That's where this comes into play. That's where this comes into play. I don't know why I said that weird, but that's where this comes into play. Now we're learning about those configurations. And you see that now chlorine 1- has the exact same configuration as argon. So 2 elements can have the exact same electron configuration if one of them is charged. So don't be freaked out if that happens. And here's another example with Re. So Re, we're not going to write all that stuff out. That's crazy. That has 4f14, etc. But I think it would be good practice for you guys to do on your own to write one with an F block in the middle. Wait, so just by looking at that, how do we know it's not argon instead of Cl1? Oh, good question. You don't. You actually don't. That's it. It's a great question. So if they give you this electron configuration and say, what element is it? They have to say at ground state. What ground state element is this? Then it would be argon. They might ask you questions, and they probably will ask you questions like this. That's a good thing you mentioned this. They might ask you, this is the configuration for an atom that has a -1 charge. What is that atom? Or what is that element? You'd be like, all right, it has a 1- charge. To get a 1- charge, you need 1 more electron. So if I take 1 electron away from this, that's the ground state. And oh, that's chlorine. Got it. So that's what they might ask. Okay, good. That's a really good question. Okay, so now let's do Re. So Re is, where is that? Over here in the middle. Go up and we have xenon. Oh, I was wrong. Before I said xenon was here, I meant krypton. Whoopsie. See, even I don't have the periodic table memorized. So xenon, right there. Now what comes after xenon? You have 6s2. Then you have 4f14. 4f14 followed by 6, or not 6. So it'd be 3, 4, 5, since D lags 1 behind. It would be 5D, 1, and this position is actually 2. So this periodic table is not the best, actually. So this is hafnium is 2, 3, 4, 5. It would be 5D5, 5D5. So if you look at this periodic table, sometimes they're written like this, which you want to know the sad truth? Not everybody could decide what periodic table is the actual correct one based on configuration, whether to put lanthanum, and actinium in the F block or the D block. Because look at this periodic table. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 elements down in the F block, not 14. The reason why is because lanthanum and actinium are not in the F block. They're in the D block. They're right there. But the confusion is some people think it goes lanthanum, or some people think it goes in terms of configuration. Some people, it's weird. Some people think the ones at these end, the LU and LR, some scientists think that those are in the D block and those belong right here in those empty spots. But a lot of periodic tables suggest that lanthanum and actinium do. But that doesn't make any sense because that means this part would be broken off and then it would be the D block after. So it's weird. It's really weird, but don't really focus on, when you're doing electron configurations for elements down here, just go by their position. Because whatever happens to this F block, it doesn't matter. The position of them is the same. Where does 4F come from? What do you mean, like start from? And yes, Eric, you're right for that. So to answer Logan's question, 4F. So 4F is you basically stick this whole thing right into here, and you get 4F. These are all. That's all these. These are the bottom ones, and 5F's underneath it. But to get to this example, so let's go back to this one, RE. So RE, we have 5D5. So 5D5, then we're going to go RE2+. So for RE2+, Eric was right that in order to get to RE2+, you have to subtract 2 electrons. Because for cations, remember the metals, they lose electrons. So it would be 6s2, 4f14, 5d3. This would be RE2+. And that would be the exact same configuration as Ta. So because you lose 2, you go 2 steps back. Okay, we should move on from this. Any questions? Because we do have a lot more to cover. We're probably not going to, honestly, we're not going to finish. All right, so let's keep going. Now, something, I'm going to get rid of this periodic table. Boop. All right. So there's this next thing that's important to learn called the Offbow Principle. Now, the Offbow Principle says you have to add electrons one by one in the way of their orbitals in order to do the configuration correctly. So it's weird. So I mean, it's not weird. It makes it ties it more together. It's the opposite of weird. So if you have beryllium, beryllium has the electron configuration of 1s2, 2s2. Basically, what the Offbow Principle says, and what these boxes are called orbital diagrams. So orbital diagrams. And orbital diagrams are just a way of writing the actual electrons in the way of arrows pointing up or down, meaning the spin up or down of an electron configuration. So you can write any configuration in terms of orbital diagrams. Why is it important? I'm just writing the arrows. The answer is because you can tell the energetic state of the element and whether it can accept or lose electrons easily. And we'll talk about that. So how to get from beryllium's electron configuration to an orbital diagram, you simply just write out the orbitals that the electrons are in. So you can write 1s and 2s. Since it's 1s2, 2s2, you fill those boxes. And the way you fill them, you have 1s, 2s. you'd go for first energy level, be 1, then 2, then 1, then 2, like that. But it gets more complicated when you get to more electrons. So this is called Hund's rule. All right, so let's just do an example. We're gonna hide this example. We'll just use a new slide. So we're gonna do the orbital diagram for carbon. Actually, no, we'll do it for oxygen, which is 2 more than carbon. So oxygen. Okay, so oxygen's electron configuration is 1s2, 2s2, 2p6. And I just know that because that's one of the easy ones. And to confirm it, the electron number. The electron number for oxygen should be 8. There's 2 plus 2 plus 6 is not 8. Wait, it should be, oh, sorry. Yeah, there is, wait, it should be 8. 4, sorry, 2p4. It's a long day. 2p4. There we go. So that's embarrassing. Now you have, so 1s2, 2s2, 2p4. That's 8. So now we can break this down into our orbital diagram. So the way we do that is we write our subshells. 1s is a subshell, 2s is a subshell, and 2p has 3 subshells, right? Because in this case, so when we're talking about these boxes, these subshells, it corresponds to the number of ml values. So here comes quantum numbers again, but it's important. So if we're talking quantum numbers, for 1s, n equals 1, L equals 0, right? ml equals 0. So just bear with me here. For 2s, n equals 2, L equals 0 again, right? Because L equals 0, that means an S orbital. So we have S. And also, ml equals 0 because L is 0, ml equals 0. Now for 2p, n equals 2, L equals 1, right? Because when L equals 1, that means a p orbital. If L equals 1, the possible ml values are -1, 0, and +1. And oh, look at that. Those values directly line up with the number of subshells. This is why I was getting at that the ml. This is why I was stressing ml before, because it comes into play. The number of mLs are the number of boxes in the in the orbital diagram, not molecular orbital diagram, that's something different, but the orbital diagram. So each one of these boxes can hold 2 electrons, one spinning up, one spinning down. This represents X, Y, and Z in those dumbbells. The dumbbells would be 1 electron would be up, 1 electron would be down, 1 up, 1 down, 1 up, 1 down. Does that make sense? Does that kind of tie it together? And if not, ask questions. If you want to expand, if you want to extrapolate that, same thing is for D and same thing is for F. D would have 5 boxes and F would have 7 boxes and 2 electrons per box. Yeah, so Alex, good question. So the 3D with the XYZ, don't really worry about the XYZ stuff because remember when we went over the D orbital, it has X, Y, or X squared minus Y squared as different planes. It had weird planes. So don't worry about it like that. Don't worry about those plain letters at all. So just know it has 5 boxes and you fill the boxes up, basically. That'll help you. Okay, so now let's get to doing the configuration or transferring the configuration of oxygen to the boxes. So it's 1s2. This means we fill up 1s2, one spinning up, one spinning down. Doesn't matter if it's spinning up or down first, as long as you have opposite directions. 2s2, one up, one down. 2p4. This is called Hund's rule. So Hund's rule is, I call it, and a lot of other teaching methods, they call it the open bus seat rule. So I'm going to fill up the electrons in a certain way, and I'll just do it first. So 2p4. That means I need to fill in 4 electrons. The way to properly do it is you do this. One going up, you skip a spot, next one going up, next one going up, then you go back, one going down. That's the correct way to do it. The answer, the upfront answer is that's the way it's energetically favorable. Okay, but why? To get into that, let's backtrack. This is where the open busy rule comes in. So especially now during COVID, this certainly applies more. If you are entering a bus and you're late, let's say you did leg day in the gym, right? And your legs are like jello. And you enter the bus this way. You're going to take the first seat you can find. There's nobody in the bus. You take the first seat you can find. And you're going to sit right there. Easy. Everybody that comes in the bus has been doing leg day, so they're all lazy. But they don't want COVID either. So then next guy comes in the bus. He's like, somebody's already taking the first seat. All right, I'm going to go take the second seat. Same thing applies for like parking lots too. Nobody wants to walk all the way back to the store. Everyone wants to park close to the store. Third guy comes in. Oh, first two are taken, have to go in the third one. I don't want to sit next to anybody because then I'll get COVID. Fourth guy comes in. I have no choice. I have to sit next to somebody. I guess I have to. So I'll look the other way, meaning I'll spin the other way so I don't get COVID. But I'll sit next to the first guy because I'm still lazy. It's the best position out of the remaining three. Next guy comes in, he goes here, and next guy gets the worst spot over there. But those are not for oxygen. Okay, does that make sense? That's called Hund's rule. Yes, you play this game on the train all the time. Exactly. Especially New Jersey Transit, you don't want to sit next to anybody. I know how that is. Well, I drive now, but back in undergrad, I would take the train to go home or go places, but screw that, especially now. Anyway, so does that make sense? Is there any questions about Hund's rule? And then same thing for d orbitals and for f orbitals too. So to do a d orbital, I'm not going to give a specific example, but we'll just draw the 5 boxes. Now it's just a bigger train. Guy comes in, sit right there. It's a bad arrow. There we go. Next guy right there. Next one there. Next one there. Next one there. Next one, start over again. Start over again. Boom, boom, and boom. That's how you'd fill it up. Okay. So we talked about valence electrons already and how they relate to core electrons. Valence electrons have the highest principal energy level. And yes, Johnny, each arrow represents an electron. The reason why the arrows are in opposite directions is because their spin has to be in the opposite direction. Doesn't matter which one's up and which one's down, as long as you have one up and one down. Okay. So electron configuration of transition metals. We kind of went over this already where, I mean, it's the same thing. So it's just the same thing, but we're using the d orbital. Now let's get into specifics of exceptions. Now, let's take a look at these exceptions and we'll explain why, based on what we just learned of the orbital diagram of why this is the case. So let's look at it. Ignore everything else. Let's just look at this period 4. Potassium, 4s1 is the configuration for the valence electrons. That makes sense. Calcium, 4s2, that makes sense. It's in 4s2. Scandium, 4s2, it goes right through it. 3d1, that makes sense. Titanium, 4s2, 3d2, that makes sense. Vanadium, 4s2, 3d3, that makes sense. Chromium, 4s1, 3d5. Now, what the hell is that? And then, keep going, 4s2, 3d5, that makes sense. 4s2, 3d6, 4s2, 3d7, 3d8. Then you get copper. 4s1 again, 3d10. Then you have zinc, which is 4s2, 3d10. So does everybody first understand what the exception is? Like, meaning, not the rules yet, I didn't go over that, or I didn't go over why. But for some reason, and this occurs for most of the transition metals going down the table, in the 4th and 9th position, 4th and the 9th position, meaning out of 10, this is the 1st position, this is the 10th position. in the D block. The D4 and the D9, what they tend to do is they take an electron from the filled up 4s orbital, or s orbital. It doesn't have to be 4, it could be 5, 6, or 7. But they take an electron from the s orbital and they fill up, or they half fill or fill up their d orbital from it. They add one to their d. They go from the s to the d. And they kind of pick an electron out. Does everybody understand that happens based on what's written here? Then I'll go over why. First thing you understand, you get the concept. Or any questions about the concept? No? Okay. All right. The reason why, we'll do chromium. So when you have chromium in the boxes, the orbital diagram, you have 4s and then you have 3d. And we'll write the 5 boxes, 2, 3, 4, 5. Okay. So you're going to have 4s2. And then for chromium, it would be, well, chromium, what you think it would be 4s2, 3d4, right? That's what you'd think it would be. But let's see what happens. Based on writing this, does anybody have any idea why that would happen? Why chromium would take one electron from 4s and put it in its empty box? Any ideas? If not, that's totally fine. This is just see if you guys are thinking about it. No? Okay, that's cool. It's late. All right. Oh, we have an idea. More stable. Eric, you're right. Daniel, not quite. But it's a good idea. Daniel, I didn't think of that. It's really good. But Eric, yeah, more stable. So the answer for all this stuff is it's more energetically favorable. And it's more, what that means is more stable. And the reason why is because having an open block where everything else is filled up already by one electron is extremely unstable. And it kind of, remember those lobes? It kind of unbalances those lobes. To have one electron in every lobe is really good. That's semi-stable. To have 2 electrons in every lobe, that's a complete shell. But to have 4 out of the 5 electrons and one's missing, that's not as stable as it could be. But what's more stable is if you actually take one of those electrons from the previous orbital and move it over to this orbital. So now all 6 of these boxes are half filled. And that's actually more stable than having 5 of them filled and 1 of them open. So that's why it does this. And it does it for, I think, so I'm 90% sure it does it for every D4 except for the last 2. And it does it for every D9 in the whole table. But don't worry about that. Just worry about the first couple, 2 or 3. So that's that. Any questions on why that occurs for chromium? And for copper, same explanation, but instead of having them half filled, it would be completely filled. So for copper, here's what it looks like. Here's the expected configuration. Expected would look like that, right? 4s2, 3d9. That's what it looked like, 3d9. But 3d is like, wait, I need 1 more electron to get to my 10. I need it badly, otherwise I'm not stable and all my lobes are crooked and whatever. So 4s is like, all right, I'll help you out. I'll put that guy over there. So now it's the 4s moves. Wait, so, oh, Logan, so why are they 4s? Oh, they just want to show. So this is the abbreviated configuration. So it's, assume you have the previous noble gas in brackets. This is what would be remaining. So you'd have 4s something, 1 or 2, and then 3d something. And then for Alex's question, what about the Zn plus ion? So that's a good question. Now, something that we learned about ions, the Zn plus ion doesn't exist. Boom, mind blown. I'm so glad you stumbled on that. Zinc only exists in a 2+ charge. That's its only stable charge. And that's exactly why. Because when you have zinc, so zinc's +1 charge would have the same configuration as copper, theoretically. But since zinc has more protons, that makes it weirdly unstable in comparison to the one with a 2+ charge. So that has a lot to do with why zinc +1 doesn't exist. That's a really good question. Okay, cool. Nice. I never got that question before. That's awesome. That's awesome. Good. All right. Extra credit. No. All right. Good job. Smiley face. Nice. All right. Move on. Let's move on. All right. Lanthanide series and actinide series. It's craziness. It's nuts. So don't worry about it. I mean, like, so here's what I'm gonna do. I'm gonna show you how nuts it is. So lanthanide electron configurations. Here we go. All right, so here's all the lanthanides, and here's their configurations. It makes no sense because this is the first, cerium happens first. You would expect it, oh, it would be 4F1, it would be 6S2, 4F1. Nope. It's 5D1 because that lanthanium comes first, then cerium. So it would be 6S2, 5D1, 4F1. That kind of makes sense. Then you would think, oh, the next one would have to be 6S2, 5D1, 4F2, since we're just adding more to the F block. Nope. In that case, we don't care about 5D anymore. For the rest of them, we don't care about 5D until spontaneously in the middle we do. For very similar reasons as we talked about for the chromium and the cadmium, no, the chromium and the copper, but it's a little bit different. So none of them really make any sense. It's complicated. And then for 5F, it's even weirder. So I'll put actinides. So here, for the actinide series, yeah, some of them, in this case, we do have the d orbital involved. The pattern is very loose, and it's craziness. So if on any exam, and I talked about this with my boss already last semester, or when I started last year when I started teaching, because I was like, hey, you can't ask questions on specifics about which different lanthanides. And she said, yeah, if we ask about lanthanides, which I think so far they haven't, but if they do, it's going to be the expected configuration. But then I rebutted that. I'm like, and this is why they probably didn't put them on the exam. I'm like, well, the expected configuration also varies depending on what table you're using because of experimental data. And then she was like, oh yeah, so maybe we shouldn't do that at all. And they haven't really put lanthanides on there. They might ask you like general questions about them, like what position, like what would be the expected, how many electrons would you expect in cerium, which is the first spot in the lanthanide series? You expect 1 electron in the f orbital, for example. So things like that, but not writing the whole thing. Anyway, I diverge. Main group electrons. We've talked about main groups already. Critical thinking, we don't have time for that. Oh, give electron configurations. Okay, so we did enough examples on that. If you're watching the video, you can pause and then do some more examples here. Okay, now let's go forward. And there's your, let's see, how many following electron configurations are correct? Oh, okay, this is a good one. So let's do this. How many configurations are correct? Now, let's just see if they make sense first. Now, calcium we did already in the previous example, where you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That makes sense to me. And calcium is right here in 4s2. Magnesium is above calcium, is right here in 3s2. And here we have, oh no, 1s2, 2s2, 2p6, 3s1. 3s1, that's sodium. That's not magnesium. This one's not correct. So far, the only correct one is calcium. Vanadium, it would be argon, 3s2, 3d3. Now, that doesn't happen. 3s2, what happens after 3s2? 3s2, and then it's nothing. Then it's 3p. So the d orbital comes after 4s. So based on that, we know that's wrong also. Arsenic, you have argon, 4s2, 3d10, 4p3. So 4p3 is right here, and I think that's where arsenic is, if I'm not mistaken. So that configuration, I think, is right. And then phosphorus, 1s2, 2s2, 2p6, 3p5. What the hell? They forgot 3s. So that's not correct either. So how many of them are correct? 2 of them. Is that the answer? Should be. Yeah, I think it's 2. Okay, cool. All right. So another question. Which of the following groups do all of the elements of the same, have the same number of valence electrons? That's a good one. So let's look at phosphorus, sulfur, and chlorine. Now, just from knowing what you learned from chapter 3 and 4, do they have the same number of valence electrons? Yes or no? For A. Anybody? Do they have the same number of electrons for A? No, good. Okay, they don't, because they're in different groups, right? Phosphorus and sulfur, or sulfur is in 6A, phosphorus is in 5A, chlorine is in 7A, so no. Silver, cadmium, and argon, definitely not. You have argon in there? No way. It's a noble gas with some metals. No. Sodium, calcium, and barium? No, because sodium is in group 1A, calcium, barium 2A, no. Phosphorus, arsenic, and selenium, that is true, because if we don't see the real table right now, but phosphorus is right here, and then you have arsenic and selenium are underneath it. Actually, no, selenium I think is over here. So I think that's not right. Maybe none of these. Let's figure this out. Let me look at the table real quick. I was looking up selenium, and the first thing that came up was Selena Gomez. I'm like, nope, not that. Nope, I looked at periodic table, and it auto-corrected to periodontist. That's the way the day is going. And yes, I am right. Selenium is, this one's blurry. Yeah, selenium's to the right. Yeah, so I was right. So it's none of these. That's good. Okay. So which of the following elements which has occupied d orbitals is in its ground state neutral atoms? Oh, so which of the following, so I said that wrong. So which of the following has d orbitals that are occupied when it's in its ground state? So let's look at barium. Barium, we look at the table. Barium is up here. Barium is like, you have calcium and then barium. So barium, it does have occupied d orbitals, right? Because in order to get to barium, you need to go through a bunch of d orbitals. So it'd be this one. And then silicon, where's silicon? Silicon is right under carbon. Nope, doesn't go through any d orbitals. Phosphorus, same thing. Chlorine, same thing. Calcium, same thing. So the answer is barium. Okay, the next part of this chapter, and we are going to finish actually, is periodic table trends. So there are 3 major trends that we're going to learn about in the periodic table, and learning the things about electron configuration would really help us in understanding this. So there's a lot of concepts, all the concepts that you learned, we're going to apply them now to trends. So the first one is called ionization energy. And the ionization energy is the energy required to remove an electron. So what that means is if something likes electrons a lot, the energy required to move it is going to be large. So, for example, the nonmetals, right? They tend to gain electrons. Since they like to gain electrons, do you think their ability, or do you think it would take a lot of energy to remove those electrons or not? What do you think? Would it take a lot of energy or a little bit of energy to remove an electron from a nonmetal in comparison to a metal? A lot. Good, Daniel. So it would take a lot of energy because like fluorine wants to hold on to those electrons, doesn't want to get rid of them. So it would require a lot of energy. So its ionization energy would be large. And this, just knowing that, would tell you the basic trend. So as we go from left to right, the ionization energy increases. So if you add, as you add electrons to the same quantum level, to the same, like going across the table, the reason why this happens, so all we know is that nonmetals like to gain electrons, but we don't exactly know why. But this is why. So as you increase electrons, the electrons are not as shielded. Wait, do not completely shield the increasing nuclear charge. Oh, so what happens is you go across, you're adding protons. Wait, this wording is weird. So electrons in the same principal quantum level are more strongly bound as we move from left to right. Yeah, that makes sense. Yeah. So, okay. So what happens is, as you go from left to right, the nuclear charge increases. So the protons increase. When the protons increase, is important. So this kind of relates to the other trends. So when the protons increase, the added protons as you go from left to right, the nuclear charge gets bigger, increasing nuclear charge. What this does is that it increases the pull of all the electrons to the nucleus. Even the ones that are added on, it increases the pull. So it increases the pull of all of them. If that's the case, then as you go from left to right, removing an electron after all of that pull is added, meaning all those protons, is extremely difficult. This is why those atoms like to gain electrons, because removing them is more difficult than gaining them. Gaining them is a bit easier. Does that make sense? If not, ask questions. I can explain it again. All right. Even so, I'll explain it again. Nucleus, positive charge. Electrons around. You have a bunch of them. All right. I'm going to go from left to right in the periodic table. Add another proton. Add another proton. Add another proton. What it does is no matter, and also I'm going to add electrons. But what it does is it draws all of the electrons in closer. Doesn't matter how many electrons you add. The nuclear force of the nucleus pulls all of them in. Because all of these electrons are now experiencing an increase in nuclear charge. So it pulls them in. Electrons that are more tightly bound to the nucleus have a harder time of coming off, and it requires more energy. That is why ionization energy increases from left to right. Okay, I think we're good there. Next one. As we go down, so instead of going, we know left to right, we increase our ionization energy. As we go down, ionization energy actually decreases. Because as you go down, you're increasing protons, but also you're getting new rings. By rings, I mean energy levels. So you're getting more energy levels. So in energy level 2, n equals 2, you have 1 and you have 2. Energy level 3, you have 1 and you have 2, and then you have 3. The elements get vastly bigger. If they get vastly bigger, regardless of the amount of protons added, the force of those protons coming in would bring them in still, which is why going from left to right makes them increase in ionization energy. But going down, they decrease in ionization energy because you're adding that extra layer of electrons that are further away from the nucleus. If you have electrons that are further away from the nucleus, they will be more easily removed, and it takes less energy for them to be removed. So does that make sense? So as n increases, just like this says, size of the orbital increases, meaning electrons become further apart, and the removal of them becomes easier. So here's a chart going over the ionization energy, the first ionization energy. So the top is helium. So it follows that trend almost perfectly. There are exceptions, such as nitrogen and oxygen. You'd expect oxygen to have a higher ionization energy, but actually lower than nitrogen. But generally, that trend is true. And here's another way of writing the trend. Increasing going left, increasing is going top right. Top right is high, bottom left is low. Think of it like that. Okay. So we notice that, well, there are exceptions too. And because of, okay, so before that, what was I going to say? Oh, we noticed that we're talking about first ionization energy. Did we get the second? Oh, no, we don't. We should talk about it. So we know we're talking about first ionization energy. There's actually second ionization energy and third ionization energy, and you can have a lot of them. Basically means what is the energy required to move an additional electron? And that energy vastly increases because once you move one electron, the thing becomes tighter. And if you move another one, it becomes tighter, becomes tighter, becomes tighter. And then when you keep removing them, when you have to go to inner energy levels, the electron becomes extremely difficult to remove. So let's look at an example. Let's do an example before we talk about the exceptions. This is important as well. Okay, so let's do, we have positive nucleus, n equals 1, n equals 2, 1, 2, 1, 2. Okay. Let's say that the ionization, so let's say the ionization energy, first ionization energy, we'll put IE1 is 20. This means it takes 20 kilojoules per mole to remove this electron, right? Ionization energy level 2 means, all right, how much, after that first one's already removed, how much energy does it take to remove the second one, which is the one right here? Usually that's a lot higher, but not, it depends on how much a lot higher. So let's say it's 35. So almost double. Remove that one. Now we only have these two inner ones. The third ionization energy. Then what happens here is now that you have no more electrons in that outer shell, you have to take electrons from a shell that is extremely close to the nucleus in comparison to the outside shell. This means that the ionization energy for this third electron is extremely greater, is a lot greater than the second one, because you have to take electrons from a place that really don't want to get rid of them much closer to the nucleus. So an expected ionization energy for the third one in this case would be like 400. The increase would be a lot bigger. And then for ionization energy level 4, which is another electron on that same level, it would be a little bit higher, maybe like 600. So does that make sense? As why as there these big jumps? And when in the periodic table you would see those big jumps is when, let's say we have calcium. This is very important because they might ask questions on it. Calcium. You remove one electron from calcium, you get to potassium. All right, there's probably going to be a little bit of a jump. You remove one electron from potassium, you get back to argon. So now you remove that energy level completely. You remove the 4s energy level, it's all gone. Now, if you remove an electron from argon, it will take an extremely large amount of energy compared to the ones of the first and the second. Oh, I made those up. Those, Logan, I made those up. But those will be given on the exam. So let's say they gave you, all right, here's a question. So I'll spill the beans. So on the 125 exam, they love to give this question. So they might give it to you guys too. So if you have a period 3 element, so period 3, we're right here, that has a first ionization energy of 50 or 40, a second ionization energy of 70, and a third ionization energy of 4,000. Which period 3 element is that most likely going to be? So the way to figure that out is you're like, all right, the big jump is when if you look at the diagram I drew before, the big jump in energy, in ionization energy, is when you remove the last electron from that entire shell. And you have to start picking from the inner shell because that's a lot closer. So let's see where, when we remove a second electron, it becomes dangerous or becomes a lot of energy required to move it. So let's look at sodium. Sodium, remove 1 electron, ionization energy is something, right? It's pretty low. And then after you remove that 1 electron, you're a neon. If you remove an electron from neon, the second ionization energy of sodium, that would be huge. So for sodium, we'd expect maybe the first one would be like 30. The second one would be like 3,000. Because you remove the first one, not so bad. Because sodium wants to lose an electron anyway. They're like, here, take it, whatever. But then neon's like, I'm a noble gas, dude. I don't lose electrons. But you have to lose an electron. It's going to take a lot of energy. That's why this big jump. But for something that has a second ionization energy also low, and the big jump occurs in the third ionization energy, that would have to be magnesium if we're talking about period 3. Because magnesium removes the first one, not so bad. Removes the second one, not so bad. When you remove the third one, that's bad. Therefore, this would have to be magnesium. Any questions on that? Does that make sense? Yeah, hopefully it does. Okay. I think that was a pretty good explanation. You can rewatch that if you want. Okay, so let's go over exceptions. Now, the first ionization energy of phosphorus is 1060 kilojoules per mole, and for sulfur, it's 1005. So if you look at where they're positioned, sulfur, you'd think it would be more, but phosphorus is a little bit more. And that's really the case for these 3, nitrogen, phosphorus, and arsenic, when compared to oxygen, sulfur, selenium. And the reason has to do with orbitals. Oh no. So here's why. Phosphorus and sulfur have these electron configurations. So if we draw them out in their orbital diagram, phosphorus will have, let's do 3, here's what we'll do P, we'll do S, we'll do, I'll put Phos, just not to get confused with the other P's and S's. We use Phos and then Sulf. 3S, and then we have 3P. So here's the 3S and 3P orbitals for phosphorus and sulfur. Phosphorus is 3P3. Sulfur is 3P4. I didn't fill those in right. So I want to do that again just to show you, just to remind you how to fill those in. So you go Hund's rule. 1, 2, 3, go back to the first one, 4. Okay, so now, theoretically, based on the trend alone, sulfur should have a higher ionization energy than phosphorus, at least for the first ionization energy. That's not true. The reason why is because of that energetic favorability of having either a half-filled or a completely filled subshell. This comes back. So if you were to remove an electron from phosphorus, it would require a lot of energy because as we talked about before, having this energy level filled or half filled with electrons, the P, that's kind of favorable. That's kind of stable. So to remove one and make it unstable is not very good. It doesn't make the element very happy. So that's not as favorable as for sulfur's case, you have an extra electron that once you do remove it would make them half filled. That would actually make it a little bit more stable. In reality, it doesn't because it's still sulfur, but the stability difference here is a lot less than the stability difference when you remove one from phosphorus, which means that phosphorus is going to have a higher ionization energy for the first ionization than sulfur does. Does that make sense? It's based on the molecular orbital or molecular orbits. Now, you notice how a lot of these trends boil down to this. I would suggest knowing what these mean, the orbital diagrams. So for example, let's take a step further. Sulfur. If I remove one electron from sulfur, we know it's not that big of a deal. So the ionization energy is like 1,000. If we remove a second one from sulfur, now we're taking a half-filled shell and removing one to make it not half-filled anymore. We know they like to be half-filled. So doing that would make it a lot bigger. So the second ionization energy level would be maybe 1,700 or not, maybe 2,000. But that jump is more than the second ionization energy level jump for phosphorus. Because for phosphorus, the first ionization is hard to do, right? Because we're taking away that half-filled shell. So the first one is maybe 1,100, a little bit more than sulfur's. But the second one, once you remove that, is not so bad. The second one, you're just removing, now that you have two in there, you're just removing one of them. And it's not interfering or making anything less stable. Well, it is making it less stable, but it's not making the half-filled, or it's not the difference between half-filled and not half-filled, if that's what I'm trying to say. So the second ionization energy for phosphorus would probably be around maybe 1,800. It wouldn't be double. It would be a little bit less than double when sulfur is double. So does that make sense in terms of those? It's difficult and a lot of practice is required, but to compare between different ionization energies based on how favorable the end product is. Any questions on that? No? Okay, we gotta continue. So, all right, next. Oh, now there's a question. None so far. Okay, cool. All right, good. Hopefully that means you're understanding it. Electron affinity. So electron affinity is the next trend, second of third trend. And it means the energy associated with the addition of an electron. So energy associated is not the same as energy required. It means it's the energy gained by, or energy lost. Well, I mean, that's the best way they talk about it. Energy associated. It could mean gained or lost, but it's the energy associated with the gaining of an electron in an atom. And the trend, well, let's talk about the trend first. So as we go from across a period from left to right, the affinities become more negative. So here's the thing. The electron affinities become more negative. That means when you add an electron, more energy is released. That's a good thing. So electron affinity, if you have a high electron affinity, that means as soon as you gain that electron, you're releasing a ton of energy to the environment, which means it makes you as an atom more stable. And it actually has a very similar trend, the same trend as ionization energy, but they mean different things. So fluorine has the highest electron affinity. And also another thing is for electron affinity, the noble gases don't count. They don't have any electron affinity. They don't want electrons. They're happy. Fluorine's the highest. So for fluorine, the energy released in gaining one electron is huge because fluorine is small it has one open spot left, and it really wants to fill that electron and become -1. Once it does, releases a bunch of energy, and it's stable. Same thing for all the halogens. And then as you go to the left, it decreases. It depends on the atomic number, right? So it depends on, how am I going to say it? So it depends on if you have a larger atomic number, meaning more protons, then adding an electron would release more energy on average. Well, yeah. So next, so it becomes more positive as we go down. All right, so the thing with that is it becomes generally more positive as we go down the periodic table, because when you're adding these electrons, the levels at which you're adding them, the energy levels, are further away from the nucleus. So in smaller atoms, you usually have a lot more energy associated with the movement of electrons. In general, that's a good rule to know. In smaller atoms, if you add or remove electrons, it usually requires more energy than in larger atoms, because once you're further away from the nucleus, there's not that much pull on those electrons. In order to gain them or to lose them, it would not take that much energy. So the magnitude of the energy released decreases generally when you go down the chart. And you can see that kind of here, where you're in the 300s, and then when you go down to iodine, you're in the 200s. But it's still, they're pretty close, because they're all halogens. They all want to gain that one more electron. All right, the third one is atomic radii. So atomic radii is basically the size of the atom. And you can imagine, does the size of the atom go up or down as you go down the periodic table? Up or down? Yes. Wait, what did I say? Yeah. When you go down the periodic table, I forgot what the question was. When you go down the periodic table, the radius goes up, right? Because you're adding more energy levels. So that makes the radius larger. What about when you're going from left to right? So let's go back to the table. Ignore this. Let's talk about radii. When you're going from left to right, what's happening? You're gaining protons. And we talked about this already with ionization energy. Once you gain protons, that nuclear charge becomes greater. And the electrons become what? More tight. So is that the size increasing or the size decreasing as you go from left to right? Increasing or decreasing as you go from left to right in size? Decreasing. Good. So as you go, so fluorine, helium, all these on the left, the noble gases and the halogens, are pretty small, because they're adding the maximum number of protons, or for the noble gases specifically, they're adding the maximum number of protons in an element that has their energy level. So neon is the maximum protons in a electron, or sorry, the maximum protons in an element that has electrons in the 2p shell at its max. So for argon's sake, I'll say that better this time. Argon's outer shell is the 3p. In comparison to every other element that shares that, chlorine, sulfur, phosphorus, silicon, aluminum, as the largest shell being their 3p, or just 3 in general, if you go across the row. Argon has the most protons of any of those elements, meaning it's going to be the tightest. There's going to be a larger effective nuclear charge on all of the electrons, bringing them closer together. That's why. Okay, so atomic radius decreases going down a period, across a period, from left to right. Increases going down a group, because you're adding more orbitals, right? Orbital size increases. So yeah, here's a good example of that. As you go, so the bottom left of the cesium is the biggest, because you only have in its row, you have the least amount of protons, which means the energy levels are more relaxed and it's larger. And also you have one valence electron. So it's going to be just out there, and it's going to be a pretty big thing. And if you're going down, it's going to have the most energy. It's going to have the most energy levels, and with the most energy levels with the least amount of protons. That's why. Least amount of protons in its class, in its period. And here's what it looks like. So it's kind of the opposite trend as ionization energy and electron affinity. Okay, so predict the trend in radius of the following ions. All right, so now we have ions. So we have beryllium, magnesium, calcium, strontium. So here, where are they? Beryllium, magnesium, calcium, strontium. Now, if they're all 2+, right? So it doesn't, we can ignore that. They're all 2+, which means they're going to be, after they lose their 2 electrons, they're going to be noble gas configuration in their electrons. But which one's going to be larger? Which one's going to be the largest? Magnesium, calcium, beryllium, or strontium? Strontium, good, because it's lower down. It has the most energy levels. And even when you remove those electrons, it does decrease the radius a little bit. So that's the thing. When you remove electrons, you're slightly increasing the nuclear force from the protons, sucking them in. So if you remove an electron, it does make the energy level get a little, it does make the radius get smaller. And then especially when you go back to like magnesium. So if you go to magnesium and you remove 2 electrons, you're removing the entire outer shell of electrons. And now the electron configuration is like neon. So if that's the case, then it will greatly decrease the atomic radii, because now you have something that has a configuration that's pretty tight. And actually, the radius would be smaller than neon. It would be shrunk. It would be smaller because you have more protons, same amount of electrons. So you even have a greater pull than neon to the center of the atom. Yeah, so strontium, yeah, we get it. Okay, cool. Consider the following orders. Which of these is the correct trend in size? Oh, I just flipped on the end. Let's just take a look. So correct trend in size. Aluminum, silicon, phosphorus. So aluminum is less than silicon, less than phosphorus, less than chlorine. Not true, because out of all of these, I can tell that chlorine's the biggest. Chlorine's the smallest, because it's a halogen. It has the larger number of protons in its class, in its period. And I think all of these are in the same period. So that's not right. Beryllium, magnesium, calcium, strontium. That's right. We just went over that one. So strontium is biggest. And then the other ones are wrong. Okay. So, first ionization. Cool. So here's one. The first ionization energy for magnesium is approximately 700. What is a good estimate for the second ionization energy? And keep in mind, it's never going to be negative. So for magnesium, remember we talked about magnesium, how you remove 1 electron, not so bad. You remove 2 electrons, not so bad. You're here. Once you remove the 3rd electron, really bad. So it's not going to be too bad removing that first electron. So what do you think it would be? Anybody want to guess? Good, 1400. Yep, it would be B. Sometimes they're twice as much, but twice as much isn't a huge jump in these terms, whereas like a 10 times jump would be huge. In this case, that would be a 100 times jump, but yeah. Okay. We're going to skip that one. Here's some examples you can do. You can pause the video and do them on your own and think about it if you're watching the video, but just for time's sake, we want to cover everything. Okay, information contained. Yeah, we kind of know that already. Metalloids, we talked about them. Yep, we know this already. We know that. Okay, so let's do one more example. We'll do one more of those examples, and then we'll do this one. All right, so which of the following correctly ranks the ionization energies of oxygen, fluorine, sodium, sulfur, and cesium from smallest to largest? Okay, for this one, I'm going to take a periodic table. So we can look at it, and I'm going to drag it down over here. Yeah. Oh, let's just take a picture. Like, here's what we can do. We can copy it because we have technology. Okay. Hopefully you can see that. So now we have, which you're following correctly, ranks them from smallest to largest. So ionization energies, right? The amount of energy required to remove an electron. So let's look at, right off the bat, I see fluorine. Fluorine is over here. It does not want to lose an electron. It's going to have the largest ionization energy. So automatically, it's either A, B, or that's it. It's either A or B. So now let's look at the next ranked. Oxygen. Well, let's just look at the answer choice to see which ones are wrong. Oxygen, that's right, because oxygen is right next to fluorine. It needs to gain 2 more electrons to get to noble gas. So to lose one, it's not going to want to lose one. It will require a decent amount of energy. Next, let's look at sulfur. Is that true? Sulfur is over here. Yeah, sulfur is a non-metal. So compared to things like sodium and cesium, which are metals, sodium and cesium, sulfur is going to want to keep its electrons. Now, so that's that. So that really answers our question. It's A. But let's look at sodium and cesium. It's important to compare those because they're both in the same group. Now, sodium, instead of just memorizing the trends, I definitely suggest thinking about it and thinking about it in the chemical terms of why it's true. That'll help you more. Because the trends, there's 3 trends to know, and you might get confused. So for ionization, atoms that are smaller and have their electrons closer to the nucleus are going to have a larger nuclear force, the larger pull of the protons. That means the ionization energy is going to be greater, or meaning the energy required to remove one of those electrons is going to be greater than an atom that's lower on the periodic table that's bigger. Bigger meaning its electrons are further away from the nucleus and have a less charge or less pull. So sodium is going to have a greater ionization energy than cesium. That's why it's in this order, because cesium is really large and its electron that would be ionized, its first ionization would be very far away from the nucleus, and the pull from the protons in the nucleus won't be that great.